Okay, for example, x minus 1 over x plus 2. We can separate this. It becomes two equations. The first one is x over x plus 2 minus 1 over x plus 2. And each one, I think, because we already know the 1 over x plus 2 in terms of power series, we already did in the example. You can exchange those into power series and then multiply with x. And then you can have both series, and then you can solve both series. Okay, so for example, this we can have okay. So each one, they have their own power series. Okay. But there will be a difference when we have the x here. We will have xn plus 1, right? Xn plus 1 because we have multiplication with x for x plus 2. So what we are going to do is we need to set up the power series so that if we have the power series, for example, we get maybe this is power series, okay. If they have different n, then we need to make the n equal. Okay? We need to state the n equal. For example, if this is 1 and this is 0, we need to make it also 0 here. Okay? So we need to rewrite the form, and then by doing so, we can combine these two together. Okay? I think I will later just showing you some additional content for all this information. Okay? But the idea behind of all these terms, okay, especially the last three questions here, this is we need to at least relate to either derivative or integrations. For example, this one, we have squared here. For obvious reasons, it's probably using derivative, but we need to take some time to figure out, and then maybe multiply with x, or maybe divide by x. Later on, we will see how the form will be looking. And for ln, we know that this will be related to the integrations. Okay? And by looking on the 1 plus 4x, you get the idea that this probably will exchange minus x in 1 over 1 minus x. Right? So maybe you can think on this. And maybe you can take the derivative of maybe you can check this, what kind of power series is it, and then check when you derive this, is it becoming this or not, or maybe looks similar, so you need to modify. Okay. Of course, it will be different if it has x at the top, right? So probably you need to multiply with something, right, to make it similar. Okay, that's the key. Later on, I think I will just give you the notes or maybe just the video just to show. Okay, now we finish on the representation of functions or representation for the power series for each functions, and then in 11.10 we will learn on this is called the Taylor and Maclaurin series. So the idea behind Taylor and Maclaurin, that is the name of the people who invented this series, is similar with what we have done before. So basically we have functions. Okay? So we have our functions, and we need to represent those functions in terms of power series. The same idea with what we have done before. But the difference is how Taylor and Maclaurin they create the series. They create the series from the idea of the geometric series. So if we look upon the power series, okay, Okay, this is the power series that we have done before. Let me just write several components here. And of course, we have a ratio. Okay. And in terms of the radius convergence. Okay. Okay, first, if we let x equal a, so that all the terms that have x minus a all become 0, right? All become 0. So we have fa equal this coefficient. Okay, so let's write. Okay. Now, if you take the first derivative, we will get a new form, right? And then we can take the derivative for each coefficient, right? Okay. So let's also do that. So Taylor and Maclaurin, it seems that the series, they start to relate the functions and its derivatives, and what's the relations behind those derivatives with the series itself. So if we derive the C1 plus 2C2 x minus a plus 3C3 x minus a squared plus 4C4 x minus a cubed, and plus, of course, still the same ratio. Okay, now this is the first derivative. And similarly, if we let the x equal a, then f prime a will be C1. Okay. Still nothing too complicated here. This is just a first derivative. Okay. And then when we take the second derivative, the third derivative, and the fourth derivative, we'll see some patterns. So let's look on the second derivative. Now, the second derivative, 2C2 becomes 2C2, and the x minus a becomes, the constant becomes 0, and the other linear x becomes just a constant. And 3C3, this is squared, and then we can take derivative, 2 multiplied by 3. It should be 6, but let me write 2 multiplied by 3. Okay, let me write 2 multiplied by 3. So 2 multiplied by 3, C3, x minus a. Okay. And then plus 3 multiplied by 4, C4, x minus a squared. And of course, we will have another one like this. And this is cubed. And on, and still same ratio and radius. Okay, and if we substitute, then the second derivative is equal to 2C2. Okay. Okay, let's try the third derivative. Now this becomes 2 multiplied by 3 multiplied by 4. C4 x minus a plus 3 multiplied by 4 multiplied by 5. C5 plus still the same ratio or radius. And also if we let x equal a, the third derivative a becomes 2 multiplied by 3, C3. Okay. Well, we can try the fourth. Usually if we write the fourth derivative, we write f and then 4 and x. Okay. Still the same. And if we let x equal a, f for a becomes 2, 3, 4, c4. I think this is interesting to see. So the second derivative is 2c2. The third derivative 2, 3, c3. The fourth derivative 2, 3, 4, c4. And if you look all these three, and maybe from the first one, the first derivative, you will see that it has certain pattern. It's 1, 2, 2, 3, 2, 3, 4, 2, 3, 4, 5, 2, 4, 5, 6, okay, and so on and so forth. So we can have, at least in general, if we have some nth derivative, we derive several times in terms of n. And if we let x equal a, we will have 2, 3, 4, some n of cn, or we can write as n factorial cn. Or we can write in terms of the coefficient itself, cn equal f okay. And also the formula is still valid if we check with the n equals 0, because n factorial is 1, so still valid. Because n equals 0 makes this becomes 0 factorial. 0 factorial is 1, so still we can use this relations. So if we have, if the function has a power series representation at A, if f of x is equal to this power series that we have learned before, in which we have known that it has certain radius of convergence, then its coefficient are given by this Cn equal Now this formula for the coefficient will be the key for our Taylor series. So if we are going to look on the power series that is defined by this power representation, if we substitute the coefficient, if you substitute this coefficient back to the power series, so see the Cn we substitute, then it's actually become a new, it seems a new series that we can derive. So and that will be our Taylor series, the Taylor series. So the expansion of the Taylor series. So let me write here. Substitute to then we will have now if you expand the sum, if you expand the series, let's start from 0. This will be FA for n equals 0, and then n equal 1 will be f prime a 1 factorial x minus a, then plus the second derivative 2 factorial x minus a squared. Let me write several times here, and then the third derivative we can write and this is what we call the Taylor series. This is Taylor series of the function f at a. So because we can exchange the Cn with this relations, so by conclusion, actually what we have learned before, all the functions that we can represent with 1 over 1 minus x, they are also can be represented in Taylor or Maclaurin later, the same series, But it is more in a general way that we can really look on the functions, and then we can set up some expansion for the series, and we can take it into this form. Okay, maybe let me go for the Mclaren series. Okay. So the Mclaren series is actually the Taylor series, but the A is equal 0. So for special case where A is equal 0, then the Taylor series becomes so we just exchange all A with 0. So this A f0 and then f prime 0 factorial, and all the terms just x and x squared, x cubed, and this is what we call the Maclaurin series. Remember the 1 over 1 minus x, we can actually see that in terms of the x, some coefficient here, okay, and then x squared, x cubed. It seems similar to what we have done before, right? So it's a general way to put our functions in terms of power series. So now you have another way to set up a series. So instead of just looking on the geometric series that we have done, the 1 over 1 minus x, we can actually set the Maclaurin series to set up the function as an expansion of the series. Okay. Now, of course, we need to look on whether the statement is true or not. So we can set up this Maclaurin series and then try to set up the functions that we have familiar with. For example, 1 over 1 minus x. Okay, we can set up those in terms of Maclaurin series. So let the functions is 1 over 1 minus x. Okay. We know that this should be equal with the geometric series x with power of n, 1 plus x squared plus dot dot dot, and the ratio should be less than 1, so it should be in between -1 and 1. So first we can set up several function and its derivatives. We can set up maybe 4 or 5 derivatives. So functions 1 over 1 minus x, okay, and then we set up the x equals 0, okay, to set up the Maclaurin series. So this should be 1, okay, and then we set up the first derivative. And still it's 1. Maybe take the second derivative. This should becomes 3. Okay, minus 2 minus 1, it's minus 3, so it should be 3. And then it should be multiplied by 2. And then multiplied by -1, -2. So it should be 1 and 2. Let me just write with the pattern. And then maybe let me get into the 0. And the third derivative, we can take this into 4, and this become 1, 2, 3. It seems that we have our formula for the coefficient. We have 1 minus x n plus 1. And then if we put 0, this should be just n factorial. And then by conclusions, our Cn is just Fn divided by n factorial. And because from our calculations this become n factorial divided by n factorial, it's just 1. The coefficient is 1. Okay. So that means if we let the 1 over 1 minus x equal with this coefficient formula, let me just write the whole formula here. Since this is just 1, from what we have done the calculations, it seems it's 1. So it seems that this is true, that this is equal to the series of x with power of n. So what I'm trying to say here is, if you have the functions, if you want to know how it can be expanded as a series, or power series to be precise, then you can just take the Maclaurin series. Okay? Just take the Maclaurin series. So how to take the Maclaurin series? First, take several derivatives of its functions. Maybe first, second, maybe fourth time. Take the x equals 0 and calculate the value and make the expansions. And from the expansions, you need to figure out what's the formula for its power series. Okay? 11.9, we are just playing with this 1 over 1 minus x. We try to maybe modify this with derivative, integral, and maybe we take sometimes to see the form, okay, to see the form. But now, we can take the Maclaurin or the Taylor series and we can represent in more general way for several functions as well. And not only for 1 over 1 minus x, but for other functions as well. But I think not all, but several functions that for obvious reasons that should be in Taylor and Maclaurin series. And today's our goal is to set up several functions for the Taylor or Maclaurin series and how we can represent in a power series. Okay. So this is Taylor Maclaurin. I hope you don't get confused on how we can expand this series. Okay. So the idea of Taylor, okay, you'll see that we have A, FA, prime A. All terms is 1, 1, 1, 2, 2, 2, 3, 3, 3. And it's the same. And Maclaurin is actually the same thing as Taylor. But the A is 0. A is 0. So we exchange A with 0. So F0, F prime 0, X, 1 factorial, F double prime 0, 2 factorial, X squared, and so on and so forth. Okay. Okay. Now the other functions that we can represent is the exponential, e with power of x. Okay, first thing, the derivative for e to the x, how many times you derive, it's still e to the x, right? So we can write in general that if we write in terms of this fn, it's still e to the x. Okay, so if we try to find the Maclaurin series and maybe take the x equals 0, this will be just e with power of 0, which is just 1. So by doing so, then power series representations will be just x with power of n over n factorial, which is 1 plus x squared plus the if you check with ratio test to find the radius convergence, you will see that it's all true for all x. The radius is for all x. Okay. The functions e also unique. Okay, if you look on this, so if we have its dy dx is still e to the x. Okay. So the property of e, we can say that its y is always the same as its derivative. Okay. So when we have this differential equation for e, then we can set up interesting way to find this formula as well. For example, if you want to let this y equal dy over dx, okay, let y equal 1. Okay, let y equal 1. Just take some time to place some numbers here. So let's just put on y equal 1. Because of the property, dy dx seems to be also 1. But if dy dx is 1, then this is wrong. It's wrong logic. So we need to add x. So that when we derive, this is 1. Okay. But then we look again the property. It should be the same. It should be the same. So we add more plus x. Okay. We add more plus x. But then when we look on here, when we derive, it seems wrong. We need to add some squared here, some x squared. So we add plus x squared over 2. So when we derive, it's become 1 plus x. But then we need to have the same, so we add more. Okay. So add more here. And again, we need to have the x cubed. But when we derive, this should be the same. So we need to divide by 6, right? 6 or 3, 2. Okay? And this is becomes 3, 2. This is become x4, 4, 3, 2, and and do you see the formula here is the same? Okay. So you can actually think from this perspective, okay, to get the e. Okay. So actually this is our e to the x. So we can set up e to the x as a series of 1 plus x squared over 2 plus x cubed over 3 factorial. Okay, but we have another question. Okay, so if we know that the e to the x is a power representation of the series, then the question will be, how can we determine ex whether e to the x have a power series representation? So what the question means is how we can define under what circumstances that we can take this into the Taylor or Maclaurin series. Of course, we need to have some requirements, some satisfactory requirements to make this happen. Okay. So that's our goal for this one. Okay. Okay, if the functions, we can define the functions as the power series, and we can exchange its coefficient with this f and a over n factorial x minus a with power of n, which means if this is a convergent, as we define in terms of radius of convergence and interval of convergence previously, then we need to define that if the series is convergent, then it should have certain property that states about its limit. Remember that if we have a series, let me write here. If we have a series of an, for example, we're actually looking on two conditions. Okay? Its own sequence and its partial sum. okay? Because we need to make sure in which end it should be ended, right? So we need to have some certain limit. Okay? We need to have some certain limit. So we are talking about its own sequence, and maybe this should be series. Sequence and the partial sum sequence. Okay. The same thing here. We also need to consider what is the partial sum. Okay. What is the partial sum for our functions? It means that, or okay, let me write in another phrase, that the f of x is the limit of sequence or partial sum sequence, I think better. Partial sum sequence. If we define the partial sum as Tn, and maybe using different integer, probably I, not n, until the n, okay? And actually the same formula, just to note that we have certain sum, okay? We need to end on several ends, right? And we can also deliver this partial sum in terms of the Taylor. And then we can end with some n in our case here. Okay, this is what precisely the partial sum purpose. We need to cut the sequence, right? Cut the sequence to some n. Okay. It's similar to what we have done in the series at the beginning. We have sequence and partial sum. This is practically the same, but the difference is we are doing it with the Taylor, now with the Taylor series. So if the functions is e to the x, okay, and we know that the t1 also from the sequence of the power series, this will be 1 plus x, right? And if we have t2, this will be 1 plus x squared over 2. And the same thing we have 2 factorial t3. This also 1 plus x squared plus x cubed. Okay, and we have more and more. We increase the n. And if we look on the graph, or maybe if you check the graph using GeoGebra or any graphing calculator, you will see that when we have 1 plus x, this is just a straight line. This is 1 plus x squared over 2. This will be a quadratic, okay, and a cube. And when you look on how it's going to be, we will get to see that. Let me check. Let me put the graph. So we start from this straight line, 1 plus x, okay? And then we increase the n, and becomes t2, this green one, okay? And t3, the blue one, is going to have the cube, okay, the cubic. And then if we increase more, we have e to the x here, the red one. Okay? But then remember, Okay, remember, as long as we increase, for example, n equal 10 or n equal 100, in reality, of course it depends on the software, how accurate the software can be, like how many pixels it can visualize into our eyes, right? But actually, in reality, if we look on the point and the line, when we increase the n, actually it never crossing the e. So it should have like never touch the e, actually. Okay. But since we are applying the limit as a concept in terms of calculus, then we can immediately remove the gap. Which means the general will be our functions is the limit of our partial sum. But in actual reality, if we learn on more about the actual subject, okay, those gap is actually the error. Okay, the error. So if you compute something into some, maybe compute using simulations when you're building something, and when you actually develop into a real world, maybe it's not exactly the same. It should have like certain errors. But of course, in many industry, if you check on the industry, maybe you can check some company, right? You will have some job fair. So if you go to industry, some certain industry, they will set some standards, some error. Okay. Like maybe in mechanical engineering or maybe in material science. I know there's some standards that's been set up by certain organizations, and usually it will be used in company, like maybe in mechanical engineering there's ASME. It is standard for mechanical engineering which is widely known, and usually it is going to be used in many cases. Like for example, if you build like turbine, or maybe build boiler in the oil and gas company, you will learn more about like which standards you're going to use. Or in case of maybe material science, you will learn how to use the standard for each product. Okay? For example, you need to build like a stainless steel. Of course, it has some certain standards. Okay? And in those standards, we will have the term error. Okay? And thus, this is actually related to those errors in general. Okay, in general. So if we look on the error is actually the difference between f and t. And we call the error in series, we call the remainder. Okay, the remainder. So the remainder, we can let remainder as Rn, as the difference between the functions and the partial sum. Or we can let the functions become plus the error. The Rn is the remainder of the Taylor series. So then by definitions, the error, by definitions, it should be, or maybe not this, maybe this error in terms of limit, this should be 0 in terms of limit. Okay. So that the functions is equal to limit of n Okay, we'll have a short break. Okay, so to prove this, okay, we need to prove whether this is true or not. Okay. So if we let the okay, so first, this is what we have done. The function is actually the partial sum plus the remainder, and if the limit of the remainder is 0, then for the subscription of radius convergence, f minus a equal less the radius convergence, then the function is equal to the sum of its Taylor series. So that's the conclusion from the previous one. But then, how we can show that this limit of the remainder is going to be 0? We are going to use this this inequality. Okay. And how to make sense of this inequality? Maybe I will show you how. Okay. So first is so let the n is equal 1. Okay. And let's assume that the value of the second derivative of f of x is less equal of m. M is just finite value that we need to take on, okay, on these equations. So we have the second derivative less equal m. So for a until a plus d, so we have some distance, some d, some interval. So we will have, okay, if we integrate the f double prime t dt less equal a x m dt. So we integrate with respect to t. Okay. And if you remember, if we did the fundamental theorem of calculus, this will result in f prime x minus f prime a less equal m and then x minus a. Or we can write in terms of f prime x is less equal f prime a plus m x minus a. In the same way, we are going to have another fundamental theorem of calculus. Okay. If you let this going to be with integrations, or if we take the integration and let the x becomes t, okay, to make it much more sense, because we are going to integrate from a to x. Okay. Okay, so fundamental theorem of calculus. Maybe I will erase this because it's confusing. Okay, and then we have f of x minus f of a less equal. This will be f prime a and then x minus a and plus m. This will be x minus a squared over 2. Now, if we rearrange these formulations, we have these terms.
But then since this is for n equal 1, because this is n equal 1, if we let the R1, so R1x is f of x minus t1x, or this becomes f of a minus f prime a x minus a. So R1x is less equal of m over 2 x minus a squared. If we are using the f double prime x greater equal negative m, then the R1x also greater equal negative m over 2 x minus a squared similarly. Or in more general, we can say that this R1x is in absolute value form. This is less equal m over 2 x minus a squared. So similarly, if you take the n equal to or equal 3, the remainder will be taking plus 1. Okay. So this is when we have n equal 1. We have 2. Okay. When we have maybe n from n equal 2, we will have 3. So this is going back to what we have here in the theorem, that it says that the remainder is actually, you need to just plus 1 from those terms. So for example, we need to approximate for several number of n, and we need to take the remainder. So for example, we have maybe 5 terms, okay, 5 n equal 5. So it means that this remainder should be less equal than 5 plus 1 factorials, and this will be 5 in power. Okay? And thus we will have some m. What is m? M is actually a number that we are going to look on. It depends on how we are going to limit our errors, how we are going to limit our restrictions. For example, if you want to be inaccurate within 0.0001, so then we can have some certain numbers. So how much m should we assume here? And that depends on how the error will be. Okay? We will learn more about this approximation later on. Okay? Later on in the 11.11. Okay? But for now, we can just focus on first on how we can deal with the Taylor and Maclaurin series, okay? How to tell the Maclaurin series, and how to at least use the series in terms of we are going to modify into other functions as well, and we need to tell whether it can be exchanged into power series or not. Okay. Okay. Now from these two theorems, okay, from this limit, okay, the limit of remainder, for the e to the x, we are going to show, or we are going to have, I think I need to charge my pencils. Okay, so if we have limit for e to the x, that we are going to know for sure that this will be equal 0 for every number x. Why? Since the series converges for all x. Maybe you can try to prove on ratio test. Okay.
And then another interesting fact is that if you have the e to the x equal the sum, if we let x equal 1, then e will be 1 plus 1 over 1 factorial and in fact this is the definition of e as well. Okay. So e can be defined using the limit, and also we can define in terms of series. Okay. And we can also define, if I'm not mistaken, I think this is 1 plus something, and then we have all the, I forgot what it's called, but e also can be defined as that. Okay. Okay, let me just go through another Maclaurin series that is important. Okay. For example, this sin x. If we want to find the Maclaurin series, then we should evaluate at x equals 0. And after fourth derivative, we will back into our sign. And if you look on how we develop this coefficient, we will have 0, 1, 0, negative 1, 0. So we will have at the odd number at 1, 3, and then 5, 7, we will have the terms into in the series. The other even coefficient, they will be 0. So we can remove them. So we can apply the Maclaurin series and this will be x minus, we will go the x cubed, 3 factorial, and then plus x5, 5 factorial, negative x7, 7 factorial, plus dot dot dot, and we can find the representation as a sum from n equals 0. Because it's alternating, we will have negative 1 over n, because it starts with the positive terms. And then since it's an odd number, we will have 2n plus 1 and 2n plus 1 factorial. This is for f of x sin x. Okay, you can do the same way with f of x equals cosine and try to make another Maclaurin like this one, or you can look on this sum of the sine, and we know that the cosine is the derivative of sine.
So which means we can derive this, and it's become a new series. So if we write down that sine x is going to have x minus x cubed plus x5 plus minus x7 now if we take derivative of this will become cos x 1 minus x squared 2 factorial, or let me write more clear. This will be 1 minus 3x squared 3 factorial. Let me write one by one so that you can see how it looks like. This is 7, and this become 1 x squared 2 factorial x4 4 factorial x6 6 factorial, and then it became a new sum for all x. If we include all the functions that we have done before, from 11.9, and if we include all of them as Maclaurin series, okay, we have several important or essential functions that you might need, okay, for future reference. We just put the function here. And by the way, I will skip the binomial series. Okay. So for our course this semester, we will not have any binomial. We'll just focus on the other essential functions. So this will be the essential functions for Maclaurin series. So, of course, the first one is the basic one that we have also done last time, 1/1 minus x, and then e to the x. Okay, sine x, cos x. I hope these two simultaneously can be studied to get all together, because I think you can just pick one and then the other one is just the derivative of it. Okay. And then tangent inverse, and then ln 1 plus x. If you look on the pattern, it's actually pretty similar. Okay. You see that x to the power of n over n factorial and x to the power of n is n. Okay. It's pretty similar. So why all this becomes an essential functions? Because they are looking pretty familiar to each other. Okay. This tangent inverse is looking pretty similar to what we have in sine. And example, this is having factorial, the tangent inverse is not. Okay.
And from here, from all of these essential functions, the other important thing in Taylor and Maclaurin series is we can develop a new series from this old reference. Okay. So from this reference, just like we did before, we can multiply, we can define, we can derive, we can integrate. Okay. So that will be the next one. Okay. We call this is the new Taylor series from the old, which means that from all this reference we can modify, okay, and become a new series. So new Taylor series from old. Let me just give you the example. Okay. So first, if you want to make functions x cos x, which means we are just having x and then multiply with the sum of the function of cosine x. So we are just exchange cosine with the sum. And this will be just adding 1 for x. And then, for example, the other one, we are having ln 1 plus 3x squared. So first, the first one, we can just multiply. I think we can do it really easy, or maybe we can define. Okay. For the second one, we have 1 plus 3x squared. The reference we have is 1 plus x, which means we are going to exchange x with 3x squared, like we did in the previous 11.9. Okay. So we know that this will be sum usually this is x, but we have 3x squared now, and we can simplify it more. And this is our new series. Okay, and other example is instead of finding the power series, we can also find the functions. If it is a new, it seems a new power series. For example, we have sum okay. For example, we have negative 1 power of n, 2 power of n, x power of n, divided by n factorial. Okay. If you would like, you can try this first couple minutes. Okay. What kind of functions this will be? Yeah, that's a good idea. This n factorial is probably e, right? But then what we can do is we can try to maybe formulate this 2 of nx power of n to make it into more satisfied form that looks similar to the e probably. But that's actually good intuition. Yeah. Yes, but it's not fully correct. It's e for 2x, but the 2x should be the negative, right? Right?
Remember that E doesn't have the alternate series. Okay, so because it's alternate series, we can rewrite this sum as this. And if we look on the E, we have, this is what we have. Okay. So if we look on the terms here, it seems that it's pretty much satisfied. It's pretty similar. So this sum here is actually E with power of negative 2x. Okay. So this becomes, so this is E with power of negative 2x or we can say the functions is E with power of negative 2x. Okay. Now, another type of questions that might be asked is you need to find the sum of the series. Should be 3. Sorry. So it could be a question that asking sum of the series that is should be having some converged value that you need to find. To determine the series, first you need to figure out how the patterns look like. You see the 1, 2, 3, 4, and it's not 52, it's 3 multiplied by 2. Okay. And then it's multiplying 1 multiplied by 2, 2, 2 with the power of 2, 3, 2 power of 3. So it's all with 2 with the power of n, right? 2 power of n. So we have n and 2 power of n. So we can have from here we can have 1 over n multiplied with 2 power of n. Okay? But then we observe that it has alternating signs. Positive, negative, positive. So this should be having a negative 1 because we start from, let's start from equal 1. Okay? So that this will be n minus 1 to make it a positive in the first term. And then we can write the sum as half with power of n over n. Okay. This is we are going to just try and check with the old reference we have. We have n, not without any factorials, right? Without any factorials. So the only way we can do that is we try to make the 2 with power of n, maybe take sometimes to take some form here to the upper parts. Okay, so we have half the power of n over n. And we look on the old reference. The one that has just n is this. Okay? Plus 1 plus x is n. And imagine that if x is going to be half, then x will be here. So it's actually 1 plus half or ln 3 over 2. Okay? So this will be equal with and so this series
is going to have ln 1 plus half, or ln 3 over 2. Okay. So first, find the new power series. Find the representation of function from the new power series, and then find the sum of the series, in which we need to have some convergence value. And the other way, we can find the limit problem. Okay. So for example, of course, if you remember what we did in calculus 1, when we have limit as x approaching 0, we take x into each position. This will be 0 over 0, right? 0 over 0. If we take x equals 0, which means this is an indeterminate form, if you remember the Logitech rule. So we can apply Logitech rule. If we apply Logitech rule maybe twice, I think twice, okay, because I will see this x squared becomes 2x and becomes 2, and we can constant. And e to the x, still e to the x, the other way, the other one will be 0. 1, 0, x, twice 0, right? So if we plug in 0, this will be 1, so it should be 1 over 2. Okay. But instead of using the Logitech rule, we can also exchange this e to the x with this expansion series that we have. So actually, in certain way, we could exchange this e to the x. And also, if you remember some problem with derivative or integrations that we have before in calculus 1, we can also try to solve those problems with the series. So if we can really get help from the series, then we can exchange to the series. So let's exchange this e to the x. Okay. So 1 plus x and minus 1 minus x, and then over x squared. Okay, now if we look here, 1 will be minus 1. Okay, it will be cancelled, and x also cancelled with negative x. Okay. So the rest will be just x squared over 2 factorial, x cubed 3 factorial, and so on and so on. And from here, we can define x squared, x cubed, and other x with x squared. So let's define all with x. So first, let's cancel out this. Cancel out this. Okay. And then divide all with the x squared. Okay. Now we will have 1 over 2 factorial plus x over 3 factorial and plus x squared 4 factorial and so on. Okay. And then since x is equal to 0, all terms with x will be 0. So we'll have half, which we are already proven that if we use Logitech rule, this is also half. Okay. Okay. So this is another way to solve the limit. Okay, to solve the limit.
make up the new power series. Second, find the function itself. The third one, find the sum of the series and take the reference on the functions that we have in the essential function. 4, we have limit problem. We can also use it for solving the problem. The other method is we can also multiply each function, or we can define each function from the essential function. For example, we need to find the first 3 non-zero terms in Maclaurin series for, let me write e to the x sine x and b tangent x. Okay. So the first part, e to the x sine x, means that we have this power series, each one, and we need to multiply both of them. And the second one, we have tangent x, which sine over cosine. And all those functions are our essential function in Maclaurin series, right? So, what we are going to do, because we have to find the first 3 non-zero, so the first 3 terms, that is what we are going to do. So, e to the x, we can have expansions. Sine x, we can have expansion. And let's multiply. And how to multiply? It's multiplication like usual, but you need to be careful on writing the terms. Okay. For example, e to the x, you can write e to the x, or maybe let's write all together e x sine x. So e to the x, we can write 1 plus x 1 factorial plus x squared 2 factorial plus x cubed 3 factorial plus, I will stop here because we just need 3 first term. Okay, we need just to find the first 3 terms, right? So maybe just 1, 2, 3. I think 4 is enough to look to observe. And sine, we will have x minus x cubed. And I think just 2 terms enough for sine. So how to multiply? First, we can set up the numbers. So this is e. Let me write the factorials in the value. So this will be 2, this will be 6. So this will be e to the x. For sine, let me write x here and plus, or maybe minus, x cubed over 9 here and plus. Okay. This is for sine. So let's multiply. So first multiply x with all 4s. So x plus x squared plus x cubed over 2 plus x power 4 over 6. Okay, and then multiply the other one. This negative x cubed over 6. So this will be negative x cubed over 6 and negative x to the power of 4 over 6. And since we just stop our term here, we don't really keep up with the other 2. So we just to look on the first 3 terms. So then we can just add these 2. We can add
x plus x squared plus
half minus
1 over 6, it's 1 over 3, right? And I think this is just the first three terms. So let's just write down this as our first three terms. So ex sine x equal this three terms. So it depends on the question. How many terms do you need to find? How many that you need to take observations? For example, this one, we don't really need to take on more terms because that will be waste our time to calculate, right? Okay, the other questions is the tangent. So tangent, we are going to have as sine over cosine, which this is going to have and since it's going to be the first three terms, we are just going to stop at the first three terms on sine and also on cosine. And then what we are going to do, we are going to apply the long divisions, like a polynomial long divisions. So x minus 1 over 6 cubed plus x with power of 5, 120, 5 factorials, divide by 1 minus x squared 2 plus x4. 4 factorials is 24 minus and then we can apply just regular division, regular long divisions. Multiply this, and then we have x minus half x cubed plus x4 24 minus, it's cancelled, and we have negative 1 over 6 plus half, it's 1 over 3 x cubed, and then this will be 5 divided 120 is 5 6 should be 30, 130 x 5, and then we have plus 1 over 3 x cubed. So we have 1 over 3 x cubed minus 1 over 6 x 5 cancel this. 1 over 30 minus 1 over 6 is going to be 230 to 330 to 15. And we have plus 2 over 15 x 5 plus dot. So we can just stop here and we take on the tangent inverse, the tangent x as x plus 1 over 3 x cubed plus 2 over 15 x 5 plus dot. And I think this will be the last sections for 11.10. So the Taylor series and Maclaurin series. The next section is about the applications, more about the approximations. Okay. There are some sections about physics, but I will skip that. We just focus on approximation because it's more calculus. It's much more calculus for our attention. So Monday, we still have one more class before long holiday. So we will have to finish the 11.11, And if we still have time, maybe we'll have to take time to set up some review. And also during your maybe either from Wednesday or Thursday, I will set up tests for you, just like usual online tests. You can just click and then you need to at least maybe prepare from 45 to 60 minutes, okay? Maybe 10 to 15 questions. That's going to be included all in chapter 11. So from 11.1 to 11.11. But I think it's more about the series, okay? The method, okay? How to take it to make out the series to be converged, diverged. I think more about that. And some of Taylor and Maclaurin. So I think that will be our session for today.